Boy. Hey. Oh, well, time to start. Time to start. You here? Time for class to begin. Welcome. This is CALC 2. And, okay. Whenever I try to open the Discord, it won't let me. I assume you're in the class and you just followed the link. Maybe it's crashing. I don't know. We'll have to sort that out separately. But welcome to second class and this semester. Okay. People are helping out. Awesome. We've got our 19 viewers. Our 19 viewers out of 33 people class. A lot of these viewers I know are just random people. Fantastic. State of our U.S. education. All right. Welcome to class, strangers. What's our task for today? We have 3 things coming up. We've got large scale structure. We're learning integration techniques. That's what we're doing. This is what we're doing for the first third of the class. The first third of the class, just so you understand, students, is gonna feel like someone's just presenting you with a little riddle in the form of just do this integral. And you have to pull some sequence of levers called integration techniques to try to crack that riddle. That is the nature of the first third of class. It is purely a puzzle solving exercise, right? It is very light on conceptual things. And we're going to give this the name integration techniques, how to do integrals. Okay, and the first 2 we're going to focus on here are substitution, which you learned in Calc 1, and we'll review it in really fast right here because I have 45-minute classes. And then the second one is integration by parts, which is probably new for you. And then, so we'll practice that one more today and tomorrow. And your homework is on these 2, basically on these 2 types of integration techniques. You can check the section attached to each homework assignment on WebAssign, and that's what you should read in the book if you want more information, or you want more examples done, or you want to read something if you're confused with the question. You can also ask each other on Discord. Much faster, much more pleasant way of learning. Okay, so let's begin integration techniques. Dun, 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 dun. Okay, here we go. Ready? First thing I always tell my Calc 2 students, we're going to learn how to integrate. How to integrate. Remember, integrate means find antiderivative, and then if we have numbers, plug in, and subtract, plug in. That thing. How to do that. So first thing the first rule of how to integrate. First rule. So write this down in your note cards. First rule. You need to write the following map of integral problems. So this here is the whole universe of all integration problems. The whole, like, you think of one. Yeah, it's in there. Okay? It's enormous. Huge universe. This universe of all problems that are all integral problems. Like, oh, there's one over here. You know, e.g., integrate x cubed. Holy crap, what a problem. X to the 4th over 4, right? We know this from Calc 1. Yeah, last x to the 4th over 4 plus any constant. Someone asked last time, what does plus c mean? It means plus any constant. Like your favorite one, 10. All of those will differentiate to x cubed, no matter what constant you put. So we just put them all as, here's all the answers. The plus c concept. Okay, so there's an integral problem. It's in there. It's in this universe. Okay? And now what I'm going to draw is the integral problems which are actually computable by us. Us meaning like humanity for like all time. I'm going to draw the ones in blue. You see I have my blue pen. I'm going to draw in blue those integral problems that can actually be cracked. Exactly. Ready? Here they are. You guys see that? You guys might need to zoom in. Press Control and plus or something like that. You zoom in, you see this small dot? Yeah, right there. The ones humanity can do. So what you need to take away from this is every time we ask you to do an integral, exactly, like not approximated or some garbage, exactly, you know that you're in that dot. And what that means is there's some clever choice of tricks that help you unravel that knot. That is gold for a person who's just doesn't know that this is the state of affairs. You should feel good when you see this because as a student, it means that the integrals that we give you are doable somehow. We just have to learn the techniques and arrange them in the right way. That takes practice. Okay, but this is the state of affairs. All right, so that's what you should never forget. So let me illustrate this with a classic example. So warning example. If someone asks you to find this integral, the antiderivative of e to the x squared. Okay, by the way, there's words here. If we don't put numbers, there's no numbers here. Let me put some question marks. Or notice that no numbers is what's called a indefinite integral. All it means is find the antiderivative, or plus c, right? There's ambiguity, plus c. Find antiderivative of this e to the x squared. Indefinite integral. Okay? And when we put numbers there, like, that's indefinite integral. I'm now going to erase. Okay. If we put some numbers there, like 0 to 3 or something, numbers? Okay. That is a definite integral. And the end result of this is a number. It's the area under that curve over the interval 0 to 3. It's a number. And the way you do it is this thing, f of b minus f of a. I'm going to just put this in quotes, where f, capital F, is antiderivative, which you had to figure out using some method called integration technique, anti-differentiation technique, whatever you want to call it. Okay, undoing differentiation technique. Okay, so here's an example of an indefinite integral. Find a function whose derivative is e to the x squared. Easy. Okay, so you should know, I'm just going to tell you, I'll just tell you with my authority. This thing is impossible. This is impossible. In the sense, the antiderivative exists. There is a function whose derivative is e to the x squared. But you just take your calculator out and look at all the things. Oh, ln, e, sine, cosine, tangent, square root, cube root, and through plus, minus, times, all those things. Just take your hand and just start jamming it like this. And do it for 30 minutes. And then put x's in there. And then circle the answer. That thing you just wrote down, that's not the antiderivative of e to the x squared. What I'm saying is that the antiderivative of e to the x squared is not expressible with elementary functions, the functions that we're used to on the calculator. Right? You have to give it its own new name. All right? So that is an example of a very innocent integral problem that's sitting outside of the pale blue dot. Okay? So there's your warning example. Now I'm going to give you a second warning example. So it's more like a fragility example. I'm just going to take the same one, and then I'm going to multiply it by x. Innocent. Just a small change in the problem. Like, it could have just been a typo between this second one and the previous one. Just a little slip of the finger. Oh, x. There's now a second x there, multiplying. Okay, this is completely easy integral. Suddenly, there's some fragility here. Suddenly, this is super easy. Suddenly, super easy. And that's because this integral falls with the technique of substitution. Technique. The first integration technique that we learn. Substitution. How does substitution work? The way substitution works is it's trying to be the opposite, the opposite effect of the chain rule in differentiation. Differentiation had this chain rule. Derivative of the outside times derivative inside. Okay? And so what you're trying to do when you do substitution is you're trying to isolate, you're trying to work it backwards. Like, what could be a good inside function? And then you quarantine that chunk out and you give it a new name, u. People like the letter u for some reason. All right, so I'll execute this integration. So here we go. The u that works here best is x squared. This part, I'm quarantining this. All right? And the reason why it works is because then du is 2x dx. Okay, this is the formal manipulation of d's. Or if you'd like, du dx is 2x, right? Everyone agrees. And then you just put that over there. Put the symbol over there. And that's how I like to write it. So I write this. This is the substitution. This is the name of the substitution. This is the derivative of the substitution to get how the dx part will get traded off in terms of du. That's read off by the second line. And what's amazing, the reason why this substitution works so well is because here, you look at x dx, x times dx, it's occurring in the original integrand. These are all products. You should think of the dx as multiplying the expression that's being integrated. So x dx is right there. So let me isolate that. 1/2 du is x dx. And now when you substitute all the variables into the u world. So now substitute, now translate. Translate the integral. Fantastic. All right, here, have some nice background music. Okay. All right. So here we go. Integral symbol doesn't get translated. X dx. That was 1/2 du. So I'll put the 1/2 here. I'll put the du way at the end because that's where the symbol du goes. Okay? Then e to the x squared is e to the u. And there's no more u crap here. There's nothing left. It's just this. And now this integration is simple. It's in a new world of a new variable. And it's, what's the antiderivative of e to the u? E to the u, with respect to u. It's that joke, oh, I just differentiated you and then I integrated and differentiated you twice. Oh, well, I'm e to the u, so that didn't do anything. It's some joke or something. Okay, so 1/2 e to the u. All right, that's the answer. I integrated. I did integration right here. I put a little star every time I actually did the antiderivative step. Every time I did the integration part of the problem. That way, students don't get confused later and then integrate again because they went on to a new page. I just remember. I did integrate. And now unravel. It's 1/2 e to the u was x squared. And then add in all the ambiguity plus any constant you'd like. Here it is. This is the antiderivative of x e to the x squared. Yeah, Grems, you're going to have to review. I can't reteach Calc 1. You have to understand my dilemma here. Okay. All right. Yeah, everybody has to review Calc 1. Yeah, yellow problem to start off. Okay. So, notice that this is an easy substitution problem. What you look for in substitution. So, what to look for? What to look for in when trying to use substitution. Okay, so you have something, some integral. I'm going to try to. I don't know. Professor Peter is an actual professor. He's in the chat. Okay, very good at explaining things. But I'm going to just try to tell you in terms of just raw feelings. Okay, someone gives you an integral. And it's got all this stuff, like, like, something, like, okay, wow, it's got some stuff, and you're looking through it, and you see, like, this chunk, like, x cubed plus 3 seems to be occurring kind of inside, like, nested. It's, like, ugly, it's, like, but it's nested in some stuff. Not just that, but when you look at its derivative, this thing's derivative, this thing that seems to be nested in several layers of functions, this thing's derivative, which for us is 3x squared, or something like it, like x squared, so off by a constant, fine, like x squared or like 3x squared or 5x squared or something x squared is being multiplied somewhere else. What you look for is that kind of conspiracy. Something whose derivative is also in the expression but being multiplying the whole thing. It doesn't need to exactly be the derivative because look what happened here. You see that x squared was all the way buried deep in the e. It's in there. Oh my god. And its derivative though is 2x, which is off by a number, constant, just x. And that's perfect, in perfect position for substitution. All right? So I'm going to try to write that in some explicit instructions for you so that you all can really understand what it is. But I don't want to tell just anyone. So everyone, make sure your screens are in incognito mode and everything so that no one can see what's happening here. We're going to go classified. This classified. Oh, substitution. Okay, so how does substitution work? For all the agents out in the field, substitution. The rundown. This. Try to find a chunk in the integrand whose derivative is also in there multiplying in a multiplicative way. Multiply manner. We need to use more proper, manner. All right. So try to find a chunk in the integrand whose derivative is also in there, in the integral problem, but in there in a multiply way. Multiplying everything sort of outside. Okay? So there's your secret. Don't tell anyone. Math is magical? You can whisper at me. Yeah. Okay. All right? Okay. So, let's see if you learn anything. All right? We're going to go over and we're going to see this substitution was the end of Calc 1. So I have to we need to pick it up as we go. Okay. So, let's go over to some problems real fast. You guys want an incoming problem? Okay. Here, you can have this incoming problem. Here you go. Got ourselves an incoming problem. And it's going to be a clicking software one. Clicking? Remember clicking, folks? You guys remember clicking?
Incoming problem.
Okay. Here we go, folks. The clicking software is on. So, class, all 12 of you that probably showed up, I told you, this is how it is. For my 45-hour insane speed class. Tell me, please, which technique is best for this antiderivative problem? Which technique? Oh. Or I can play something. I can play Jeopardy. Key change? Okay, fantastic. 100%, absolutely. How many people clicked? 27 people clicked. Billions of times. Perfect, got it. You get it. And now I'm just going to tell you what you already know, what you know, because you got it right. So let me just confirm that for you. Yes, indeed. Correct. Oh, you get your little, okay. You solved it? Here you go. Here you go.
We are going to make America great again.
There's a handshake. It's a handshake. Just made friends.
I'm really rich.
Okay, ready? So substitution, indeed. Substitution makes this integral just crumble. Okay, let me get that garbage thing off. Okay, so here we go. You, meaning quarantine out ln x. Then look, when you differentiate it, to get what du and dx are related, how to translate out the dx symbol. Okay, wow, perfect. Because you all remember that the derivative of ln x is 1 over x. You remember that, obviously. Okay, so there you go. You've got yourself prime position because this thing is secretly 1 over x times ln x. And here you go. You got your thing that you quarantined out. Its derivative is still showing up in the expression and in a multiplicative way. 1 over x times. Perfect. And so when you go, you translate this out, it'll become u ln x, right? 1 over x dx, that whole thing is just du. And this is the best integral in the whole world. And then you just unravel it. Plus c. It's indefinite. It's not an area under curve in a definite region. So you're giving me all the potential antiderivatives of ln x over x. Okay, fantastic. So you just totally aced that one. All right. So going back to class, let's all get up and go back to the lecture, because I just showed you 2 relatively easy substitution problems. I'll show you another one that some people get stuck on. So here's a troll. Some people get stuck on this problem, all right? And I'll make it definite if you want, like, okay, 1 to 2. We're not really concerned with that. That's just going to be plugging in numbers at the end and subtracting. But what we're focusing on is the technique of integration itself. Okay, some people will spend years trying to solve this problem using like integration by parts, the next technique that I'm going to show you. Okay? They'll just say, oh my God, how do you do this? But let me just show you how this one crumbles. It's really great. This is secretly a substitution problem. Substitution. Works. What you substitute is the whole thing that's in the square root. Quarantine this here out. And then differentiate the translation. Okay, du equals just dx. Because the derivative of x plus 1 is just 1, right? Obviously. Okay? And so, brilliant. This looks like it's not like perfect, you know, like the other ones fit perfectly together, but let's just see where it leads us. It's kind of interesting what this does. So when I translate, forget the numbers for now. Just you know what? Forget these for now. Forget it. I just wanted to show you that, you know, you can have numbers there. They're not the focus. Okay, so the actual integration part becomes, okay, x times the square root of u, x square root of u, dx gets traded for a du, perfect. This makes no sense, right? Well, this is hybrid between x's and u's. I need to translate all the way into u territory. That's what you're substituting into a different variable. Okay, to do this, you isolate x in the translator. This then means that u minus 1 is x. If I did the math, this is just some math. Okay? And so you put that into where x is. Brilliant. And then some of you might be very confused. Like, why is this better? It's better because of foil, whatever, distributive law. Look, I now do this and that, right? This is this. Okay, so this is u times the square root of u minus the square root of u du. Okay, here you go. This is what we got. Why is this better? Because principle. General principle. Ready? You guys ready for a general principle? If you can get powers of the variable in the integration expression, you're good to go. principle. Try to get to x to the n powers of x. Or u, or whatever your variable is, t. So right now it's got all that square root garbage. Square root is just u to the 1/2 power. Write everything in the power way. So you get this. U to the total of 3/2 power. Because it's u to the first times u to the 1/2. And those add up to 3/2, those exponents. Minus u to the 1/2. And now remember, when you're integrating x to the n, or something variable to the nth power, you have the anti-power rule, right? Anti-power rule. The backwards of the power rule from differentiation. Something like that. You raise the exponent by 1, and you divide by that bigger number. Okay? Now you just do that. These, you're home. This is put this on your note card, number 7. Highlight it green so that you learn it more on the bottom left. Okay, so this becomes u to the 5/2 divided by 5/2 minus u to the 3/2 divided by, you have to squint here. This is just math here. 3/2. Oh, then you do some more. You don't have to do this, but it's like you can if you want. I don't know why people don't like fractions in the fraction. I don't know. Some people, some bureaucrats, some big government bureaucrats just telling us can't put a little fraction underneath a fraction. You got to undo it. Garbage. Okay, now just unravel it. Okay, 2/5. What the hell was u? U is x plus 1. X plus 1 to the 5/2 minus 2/3. X plus 1 to the 3/2 plus any number you'd like plus 10,000. All right? Or c, just plus c. All right, so that's the antiderivative of x square root of x plus 1. Oh, right. Then we were supposed to do 2 to 1. Right. Oh, oops. Oh, right. We were supposed to do this. Oh, sorry. Okay, so what you do is then you plug in 2 into, let's give this awesome, amazing answer, purple, into purple. And then you put a minus sign, correct? And you plug in 1 into purple. And then you circle that number. Oh, so it's going to be like, wow. Whatever, it's some number. 2 to the 5/2 times 2/5 minus 2/3 times 2 to the 3/2. Okay, not bad. Minus 2/5 times 1 to the whatever. It's just 1 minus 2/3. Okay, that's your answer. This is the answer. This is the answer. Done. For the definite integral. That's the answer for the definite one. But of course, the entire meat of this answer is in the indefinite part, the actual integration part. And troll, this one might not look like it's got too much nested stuff happening, at least for some people, but it's good. There's a trade-off in swapping out the x plus 1 for just one variable, like u, one thing, not a thing plus another thing. That is what causes problems in this integral. Yes, x plus 1 was on the inside. Did I not write that? Yeah, okay. Wow, okay. That's substitution, folks. All right. We'll see more examples of substitution here in a second. Okay. So the second thing, so now what I need to introduce is our second technique. Second technique. It's called integration by parts. All right? And here's what it tries to be. It tries to be the opposite of product rule when differentiating. So let's review the product rule. The product rule said that if you have two functions, u and v, u is sine x and v is x cubed, and you multiply them. Okay, x cubed times sine x. Okay, whatever. Put some random functions if you need it. U times v, if you do that prime of it, meaning differentiate, well, you don't get u prime times v prime. Never do that. No. You get u prime v plus u times v prime. Derivative of the first times the second plus the derivative of the second times the first. You do one at a time, multiply the other, without differentiation. Okay, so for example, this thing's prime would be like cosine x times x cubed plus 3x squared times sine x. Brilliant, for example, e.g. Okay, now what we're going to do to this product rule is we're going to isolate one of these two summands, the two things added on the right side. We're going to isolate it out, okay? Okay, so what we do is we'll subtract this one, say, out on that side. And so what we get is u times v prime is, so I brought that over, is u times v all prime minus u prime v. It's just a tongue twister, but I'm not doing anything fancy. Just manipulating. Okay? All right. And now, I'm going to slap integral signs on both sides. Now slap some integrals. Some integral sign on both sides. And look, I'm going to get this thing. Okay, let me write it. Okay. When you integrate a subtraction or an addition of functions, you can do them separately. So I can just put the integrals separately. Okay, awesome. And now what you do is you squint at this middle one. A squint here. Squint. What's happening in the middle one is u times v is first getting differentiated, and then it's getting integrated. So those are opposite effects, right? Those are opposite procedures up to a constant, which we're going to put a plus c at the end anyway, so forget I just said that. Those are opposite. Integrate, then differentiate, or differentiate, then integrate. You're going to, up to a constant, get your same function back. So if you squint, you can just replace this with u times v. Nothing, just itself. And so what we get, we just bring it down, is this funny formula that the integral of u times v prime is u times v minus the integral of v times u prime. And then what you do at this stage is you put a box around this. You put a box around this and you call it, you put it in a textbook and you charge lots of money. But what you do is you call it integration by parts. It doesn't look like it's useful at all, but what you have to know is how to read this box. Integration by parts. If you do this, put box around it, put it in a book, you'll make hundreds of dollars. Okay? All right. So how do you use this formula, integral of u v prime minus blah, blah, blah. How do you use it to your advantage when trying to integrate? That's what we're going to learn here in a second. Okay. I just want to say quickly, notation-wise, you might also see it written because it saves ink so that you can make $100 more. You might see it like u dv equals uv minus the integral of v du. V times du. Don't worry. We're going to learn how to use it, and then you'll know what each of these little pieces mean practically when you're doing a problem. And so what I'm going to do here is I'm going to do an example. We have to do an example right away. Okay. So, instead of ln x over x, I'm going to do another example. Now you look at this and you're like, okay, hey, maybe substitution works. Yeah, it's not gonna give you the derivative part happening in a multiplicative way. The multiplicative way manner part sucks in this problem because the 1 over x is not just present, it's x to the first power, not x to the minus first. Sucks. But here's how someone who knows integration by parts approaches this. First, does a substitution crack this thing? The one that I'm thinking of doesn't really do much. Correct. Okay, I see that. Second thing I observe, there's a product in the integral. These are the hints. When you see a product in the integral, you should start thinking maybe parts will work. Think maybe parts. Okay, but maybe also substitution. All right. So maybe parts is going to work here. So how the hell do you use it? The way you use integration by parts is the following. You pretend in this formula that this is our integral. You hope that you can fill in u and v so that that left side looks like our current integral, and so that the right side integral part is hopefully easier. Hopefully this one, you hope. Integration by parts is an expression of hope. It's an expression of trading off our current integral for hopefully a better one, where you hope that this side is easier and doable. I'm going to execute this brilliantly here in a second, right here, right now. We're going to do it. Okay, so how do you look at it? You got to think of this as one function times the derivative of a second function, v. So we need to assign u and v. Oh, God. Okay. So you can just start randomly. Maybe u equals x and v equals ln x. Okay. No, u and dv. V prime equals ln x. Or dv equals ln x. Okay. I like to keep my dv and I like to keep the symbols systematic. Just you'll learn it when you see how I do it. Okay. So look, I tried to make this be u, and I tried to make let's color code. I tried to make green be u. U is green. Oh God, green. Okay, and then v is yellow or yellow. Okay, yellow. But v prime, I tried to make v prime be the rest of it, so that u times v prime is exactly the left-hand side of our integration by parts formula. I just tried to align it. Okay, but then out of these, you then tease out what u prime and v are. Okay, then so once you write these down, you write this down, you guess maybe this, question marks, then you fill in the rest of this. Du is just 1 times dx. Or u prime is just 1. Different notation, same thing. I'm filling in this part now of this integration by parts formula. Okay? Now the problem is I'm given v prime. Look at this problem. I'm given v prime as ln x. And I need to tease out what the hell is just v. Because just v is showing up right here. Okay, I need to fill out, I'm just filling in the blanks in this formula. Okay, where I've decided to assign u as x and v prime as ln x. And the problem here, I'll just tell you, is we don't know what the hell v is. You know the derivative of ln x, but you don't yet know the antiderivative of ln x. So this sucks. This sucks. So then I just start over. Maybe I should assign u to be the other half and v prime to be the other one. So maybe I start over. Maybe u is ln x and dv is x dx. Look how the trade-off works. If you have to go, just go. Watch the rest of the calculation afterwards on the VOD. Just go if you have to go. All right, I'm going to do the rest of the calculation. If u is ln x, what's the du part of the integration by parts formula? We know how to differentiate ln x. It's 1 over x. We did that earlier in the class. That's awesome. You see, we were more easily able to fill in this 4 pieces of information chart. U, dv, du, and then v. See, v is like its own little integration problem, because we know its derivative is x. So what is it? Well, it's a power rule, general principle. It's great. Powers are great. X squared over 2. Brilliant. So now I'll fill in the integration by parts formula and check out how awesome this is. I'm talking to people who've never taken this before. All right, so integration by parts. Okay? The integral of u dv, right, is u times v minus the integral of v du. I used the other notation. Fine. Okay, so just put them in. We'll get our integral, the one that people were asking about earlier, is, I just stick this in, look, u and v. Okay? I swapped the order, u and v, u times v, that, minus, big old minus, a trade-off, hopefully a better integral. Let's see. V is x squared over 2, and du is 1 over x dx. I'll get to questions in a second here. Oh my god, but this is brilliant. This is really good. This here is amazing. You see, because you do some math to it, like this and then like that, you know? Do that math. It's just that. And that's really great. It's just a number times x. Number comes out, and so you get, let me not write with the eraser. Let me try writing with the writer. This is x squared over 2 ln x minus 1/2 of the integral of x. And x is a power rule, anti-power rule, x squared over 2. Holy cow, this is incredible. I can't believe we actually got through this. X squared over 4. And then, of course, any number you'd like, because it was an indefinite, no one gave numbers, and you have to give me all the antiderivatives. So this atrocious, crazy thing, if you were to differentiate this, you can check it. if you were to do prime to this, differentiate it, you would get, after all this immense algebra, x times ln x. Okay? So it's a cool trick. Integration by parts is a trade-off. Your left-hand side of this equation, integration by parts equation, you try to arrange your integral to fit that. You assign what u and dv will be. You have to choose that. Some choices suck. The other choices can get you through. We witnessed that in the last problem. Then you fill in these little pieces. And what you hope for, what needs to happen, what you hope for, ideally, is that this is a better problem. Hopefully. And then you go and tackle that better problem. Okay? Using all the integration techniques we will learn. All right, so that's my first integration by parts introduction. Friday will be all integration by parts problems so that you get practice. And there's tons of practice in the textbook on the back of this section called integration by parts. You can test your hand at just rote calculation. But now I'll try to address questions. Okay. Where does integration by parts come from? Product rule. You can watch the VOD. I showed you where it descended from. It comes from the product rule in differentiation. Okay, thank you all those people who followed. That's okay. Only one of you, two people. Thanks. Okay, never mind. I don't even thank you. Okay, what else? Any questions? Let's see. Let me go back and see if I. Oh, maybe I made a mistake in. I did it correctly. God damn it. Okay. That's right. Okay, people are just great. Gath is a brilliant streamer. You should not say that. Okay. Bobo. Bobo is a VIP. Hold up, BMP doesn't even have to come to campus. Damn straight. Damn right, Phobo. Phobo is an above average student from previous classes. That's my letter of recommendation. They are above average, and they carried the class. Probably first half of last class, definitely. Phobo carried. Yeah, and Phobo actually carried the Calc 2 class too, the second half. And oh, yeah, hi Sarah. Yep, good to see you. Phobo always carried a note card. If you watched him like walking on campus, like little note cards would just come flying out of his backpack. And actually it was a fanny pack, right? Phobo wears a fanny pack. And like while he's running, like he uses one of those things that roll forward when you lean forward, and he has a fanny pack, and he's zipping through campus, and like note cards are just flying out of his fanny pack. Okay, yeah, Bobo, you get a shungite for sure. Gath is our teacher's pet. She just redeemed teacher's pet at the end of lecture. So Gath, you can be teacher's pet. You invented the concept of teacher's pet, if I recall the history correctly. There are 38 people still here. Class, you can get the hell out of here. Go. Don't go anywhere, actually. Yeah. Hey, maybe, try not to go to a bar. Have you tried that? It's not that great. It's like loud, it's dirty, and everyone's just trying to everyone's insecure. Stay secure. Learn integration by parts. Flex this thing. Yeah, don't go to the bars, you idiots. Yeah, we made national news for that. We make national news for that and football. Never for Calc 2. Let's try to make national news for CALC 2. Oh my god, this university is actually a good university rather than a football club with a bar attached. I don't know, maybe we can try. We can try to turn this thing around. Our boomer parents made our reputation football and bars. Let's turn it around. Okay, yeah, don't go anywhere. Sit there and practice with your brain, with your friends in Discord. Go. Amazing opportunity. Let's do this. Okay, next. You will drink to that. You see? Yeah, every time. Okay. Yeah, drink milk. Drink milk. Anonymous cowboy. Oh, office hours? Office hours. I need to set them. I don't know. It's either Tuesday. Hey, mathematics mama. Mathematics mama, you there? Type yes, I'm here. Okay. Since you asked first about office hours, I want to ask you, are Tuesdays and Thursdays good for you? It's all on you now, since you're the person who asked for it for first. Tuesdays or Thursdays? More suspense. Okay, let's do this. Okay. What time? No. Just tell me if the days are good. Like, are you completely shut down on Tuesdays and Thursdays? Oh, you're... Okay, so if I said Tuesday or Thursday afternoon, meaning vague, you have no hour and a half slot. Is that correct? Yes? Wednesdays. Oh, so both of them are busy. So how about Wednesday? Dingy washcloth and math mama. How about Wednesday later in the evening? Because dude, look at me. I'm sweating spheres. I have to like recoup. Wednesdays later in the evening. Yes? Okay. So that's when I'll set office hours. Not this week, because I won't have everything together. You should directly email me, Math Mama and Dingy, if you have questions, concerns. Just directly email me or direct message me on Discord. That's probably faster. So go ahead and ask me directly if you have concerns and so on. But starting next week, we'll have office hours on Wednesday in the evening time, and I'll set a time and send an email when I figure it out. Friday nights at Coyote Ugly. I can only assume that Coyote Ugly is one of these just cesspools of just alcoholism. Is that okay? You can go there and you can just blast this stream at the bar. Just go into the middle of the insecurity, find the most insecure spot in the bar where people are trying to show off the most, macho and all that, and then just take out your laptop and blast this stream. All right? You do that. Yeah, I'll see you then. Under 21? Yeah, you really think I believe in that students? Dude, I went to school here. Strock. I understand how it works, yeah. 21 is just some concept. Okay, awesome. Yeah, we don't do that kind of disrespectful chatting. If you do that again, Skinflute, you'll be banned. Good, intelligent humor is what we're all about here. Okay, awesome. Let's go. Let's try to appeal to our better angels. Better angels. All right. Enough of that. Office hours will be Wednesday evenings. And at least for now. And maybe class revolts again and says, oh, no, it should be Friday. Because that's the day before homework is due. Okay, but that's enough of those logistical things for now. We'll deal with it on Discord, the proper means, not in front of this all 35,000 people, this auditorium. That's not a proper way to deal with this class logistics stuff. Okay, so with that, I'm going to say that everyone is, Okay, everyone is, this is wrapping up. I think I've addressed everyone. Dr. WD40 was here earlier. There should be a shout out for Dr. WD40. He's definitely... Okay, Quintuple A redeems bike till the heart explodes while he sees that I'm sweating like crazy. Quintuple A is a troll. Oh yeah, of course, Guru. So for Quintuple A, bike till the heart explodes, this is how we're gonna end stream. Ending stream like this. This is the end. For Quintuple A, a former superstar in a previous class, CALC 3. This one's for you. Alright, today we learned substitution, or we reviewed it, and integration by parts came out as the second integration technique. How many integrals can we do? That's our basic question. In that pale blue dot, how much territory can we as a class cover? And I'm slowly revealing to you some tricks that you can use sometimes. When you use it and when you don't depends on how much you practice on your own. Not in a bar. At home. In Discord. Practice together. Alright. Here we go. Bike till the heart explodes. Look at the pace. The pace is insane. Wow. Okay. Okay, my thighs. Okay, my thighs. Okay, my thighs. My thighs giving out. Okay. So what do I do with all you people? Well, I gotta stick you somewhere, so I'm gonna see who's educational and online right now. Let's see. Tired? Yeah, I mean I just got tired. Yeah. I don't know, that was at least 10 minutes, Shaq. Okay, let's see. Who is educational that's on? I like to dump people into Melkos every now and then. No Melko. Hey, is Professor Peter on? No, some other professor. Dude, what are all these professors suddenly? Who is Professor Broman? Professor Broman is playing Fall Guys. Hell no. Oh yeah. Ty. Go ask Ty some math questions. Great. Go ask Ty some math questions. Alright? Be respectful. Represent our stream, with dignity. Don't embarrass us. Let's go start that raid. Go say hi to Ty. Math PhD. Just answers any question you have. He'll answer it. Or he'll... Perfectly. No pressure. No pressure, Ty. Okay, I'm gonna press raid now. So good goodbye. See you on Friday. Watch out for the office hours email that I'll send once I figure out the exact times on Wednesdays that I have energy to do this. Okay, good. And thanks to Math Mama and Dingy Cloth, or whatever his name was, or her name. Bye, okay, bye, Sarah. Yeah, be good math ambassadors. Open Set is another math luminary in the chat. Okay, go. Raid. Click raid. I clicked it. And unhost. End.